Hello, everyone. In this video, we're going to be covering example 1 from the notes on section 1.4, the derivative function. So in this example 1, it says calculate a formula for f prime of x if our original function f of x is equal to x squared minus 2. Then sketch the graph of f prime of x in the diagram to the right. So what we learned in section 1.3 was the derivative of a function at a point. So we can recall from our notes that the derivative at a point A is given by the formula, the limit as h goes to 0 of f of a plus h minus f of a all over h. So recall what we're computing here is the slope of a secant line between a and a plus h. And we're taking the limit as that interval h goes to 0. So here, this derivative is for point A. If I wanted to instead expand this definition to be for a function, meaning I want to find any value, I want the derivative at any value, not just a, well, then what I can do is replace this a with an x. So everywhere that I see a, I'm going to put in an x. So I'm going to erase that and fill that in here. So what that looks like is f prime of x as a function. So give me any x. I'll compute the derivative for you, and I'll compute it by using this formula. Limit as h goes to 0 of f of x plus h minus f of x over h. So you might be thinking it's a very subtle difference, and that's right, it is. I'm just changing notation here. Rather than inputting a, I'm inputting x. The reason why I'm doing that is because typically a in math is used for a constant, meaning it's representing some unknown that doesn't change, while x represents a variable, meaning it's made to change, vary. So I can plug in any x here and compute the derivative at x. Okay, so let's work out this limit for our particular example. So our function f of x is x squared minus 2. So I'm going to fill that in for us. So I'm computing the limit as h goes to 0 of f of x plus h. So into x here, I'm going to plug in x plus h. So that looks like x plus h squared minus 2. Now I'm going to subtract just f of x. So now I'm going to subtract, use a lot of parentheses here to make sure I don't drop a negative, x squared minus 2 all over h. So just to highlight what I'm doing here, f of x plus h is x squared plus h squared, x plus h squared minus 2. And then f of x is x squared minus 2. So there we filled in our formula there. So now I'm going to multiply out this x plus h squared. So next line, we have the limit as h goes to 0 of, so recall x plus h squared, I have to FOIL. So we can do that on the side of our paper here, just to see how that goes. So firsts are going to be x squared. Outsides are going to be h squared. Insides are going to be hx. Outsides are going to be hx. So what that looks like is x squared plus 2hx plus h squared. So I'm going to fill that in for this first term here. So that looks like x squared plus 2hx plus h squared minus 2. That's everything in yellow here. Now I'm going to subtract, again, x squared minus 2 using parentheses here. So I keep my negative in the right place. All right, I'm going to clean this up a little bit, erase this side work. And now I'm going to combine like terms in that numerator. So step number 1, I can factor in this, or distribute in rather, this negative symbol. So by removing those parentheses, I'm going to bring that negative into each term. So it's a negative, and then this negative becomes a positive. Okay, so now let's identify like terms. So I have an x squared here and a negative x squared, so those are going to cancel. I have a -2 and a +2, so those are also going to cancel. And so what am I left with? So now I'm just left with the limit as h goes to 0 of 2hx plus h squared all over h. So notice each term in the numerator has an h being multiplied in it. So I can factor out an h. So the limit as h goes to 0 is equal to 2x plus h times h over h. Now I can cancel that h from the numerator and denominator, and I'm left with the following. The limit as h goes to 0 of 2x plus h. And now there's nothing wrong with plugging in h equals 0 here. Recall, I can't plug in h equals 0 up here because that would mean I'm dividing by 0, which we cannot do. So then I can just compute this limit to be 2x. My answer here is 2x. So that means in final, what we've computed is the derivative, the derivative f prime of x is equal to the function 2x. So now let's go ahead and sketch that on the same set of axes. So 2x is just a line going through the center, has a slope of 2. So I rise 2 over 1. So I'm just going to draw some points first on my curve and then sketch in the line. So my derivative as a function looks like this line. And so just to recall, what are the output values, or what are these values representing on my derivative? Well, the values, the output values, represent the slopes of the tangent lines of my original function f. So we can see similar observations as we made in the first example, or the preliminary example. My derivative here, f prime of x, crosses 0 when we have a horizontal tangent line. My derivative is positive above the horizontal axis when my original function is increasing. And my tangent, or my derivative rather, is negative or less than 0 when my tangent lines have a negative slope or when my function is decreasing.